So yesterday what did we study? So yesterday we completed the basic things, that is the cell membrane, right? Cell membrane we completed, and very importantly we also up till now have completed the various transport processes across cell membrane, right? Now we today come on to our next important lecture, that is our resting membrane potentials and action potential. ठीक है, resting membrane potential and action potential. Now again this is one of the most expected LAQ. ठीक है, one of the most important expected LAQ. It is very important और ये आता ही है. Especially the question which you get is the ionic basis of action potential. Ionic basis of action potential. और आपको एक और क्वेश्चन आता है, generation of RMP. What are the factors that affect the generation of RMP? That is the resting membrane potential. So in this particular area, what is important is, or what are your learning objectives, or what I called it as must known competencies. मतलब ये हमको आना ही चाहिए. This is, you have to know the concept of Nernst potential. ठीक है, उसके बाद you have to know how do you generate the resting membrane potential, what is the contribution of the Nernst potential and the GHK, that is the Goldman-Hodgkin-Katz equation, to the RMP, and how is the action potential, what are the phases of the action potential, what is the ionic basis, and what are the properties of action potential. तो ये सारा का सारा is going to be in the form of LAQ to you. ठीक है, so let's get started with this topic now. Now you know that the first important concept is that you should know that there are differences in the concentration of the ions in the ECF and in the ICF. This also comes in the form of MCQ. For example, most common या major ऐसे आ सकता है, what is the major cation of ECF, ऐसा आ सकता है. Similarly, what is the major anion of ICF, ऐसे करके. So this is one of the most, I mean, question which is commonly asked as a one-liner MCQ to you. So अगर हम लोग देखेंगे ना, we just need to remember this image, तो बहुत easy हो जाता है अगर हम इस image के through करते हैं. तो आप देख रहे हो कि this is ICF. ठीक है, good evening Mudit, good evening, and please whatever queries you have keep on putting so that I also get acquainted with what are the doubts. ठीक है, so this is the ICF and this is the ECF, right? So आप देखो आपके ECF में तो आपको दिखेगा कि ECF में the major cation is sodium, right? So in the ECF the major cation is sodium and the major anion is chloride. So what are the major ions of ECF? It is sodium and chloride. Now if you come into the ICF, the major cation is potassium, right? The major cation is potassium and the anions are phosphates and proteins. ठीक है, the anions are phosphates and proteins. अब ये भी आपको पता होना चाहिए कि calcium concentration is more in the ECF. ठीक है, calcium concentration is more in the ECF. Bicarbonate concentration is also more in the ECF. Calcium भी ज्यादा है, bicarbonate भी ज्यादा है. And interestingly, magnesium हम लोग हमेशा miss कर जाते हैं, हमेशा. That means the magnesium concentration should also be known that it is more in the ICF. ये हमेशा हमारा miss हो जाता है कि magnesium concentration कहाँ पर ज़्यादा है. So the magnesium concentration is more in the ICF. Now, one more MCQ I will tell you over here. What is bicarbonate? It is the major buffer of ECF. ठीक है, it is the major buffer of ECF. और इंट्रासेलुलर में which is the major buffer, दो चीजें हैं यहाँ पर, एक तो फॉस्फेट्स है और एक प्रोटीन्स है. अगर हम देखेंगे तो concentration of the phosphates is more than the concentration of proteins. ठीक है, but proteins are the major or the important buffers of ICF. ठीक है, The proteins are the major buffer or most important or the essential buffer of the ICF. Okay, so these are the important things to be considered when we are considering the concentration of ICF and ECF ions. Now, next very important thing to understand before you understand the concept of resting membrane potential or you understand action potential, तो आपको मैं ये बताती हूँ कि channels क्या होते हैं. We have seen that the channels are type of proteins. They are type of integrated proteins. That means they are kind of integrated proteins means they are going to pass through the entire thickness of the cell membrane. And if you look into the structure, अगर आप इनका structure देखेंगे तो you will see that they are just kind of tubules. Okay, they are just kind of tubules or tubular pathways which are passing all the way between the ICF and the ECF. So they permit the entry of the ions either from the ECF to the ICF or from the ICF to the ECF. ठीक है, या तो अंदर से बाहर जाएगा या बाहर से अंदर जाएगा. So they're kind of tubular pathways, right? Now these bear a very important property that they are very selective. ये सबसे ज्यादा important property है इनकी कि ये बहुत ज्यादा selective होते हैं. मतलब पोटेशियम वाला सिर्फ पोटेशियम को अलाउ करेगा, सोडियम वाला सिर्फ सोडियम को अलाउ करेगा. सो हाउ इज दिस पॉसिबल? सो यू कैन सी दिस इज अ वेरी गुड फिगर विच शोज अस द सिलेक्टिविटी फिल्टर. Right, it shows us the selectivity filter. So you can see that this is the selectivity filter and this is a channel for potassium. It is supposed to be a tetrameric channel for potassium. Now if you look, the molecular size of potassium is more than the molecular size of sodium. इसका मतलब potassium actually जाना difficult है as compared to sodium, लेकिन फिर भी potassium easily क्यों जा रहा है? What is the reason? Now the hydrated ion of potassium, ठीक है, the hydrated ion of potassium will pass through this pore loop and you will see that the pore loop has got a selectivity filter. ये दिख रहा है आपको? This is selectivity filter. तो इसके थ्रू ये अंदर चले जाएंगे. सबसे important क्या होता है कि the selectivity filters are actually carbonyl groups. They are carbonyl groups. तो जैसे ही potassium ions will pass through the selectivity filter, जहां पे कि carbonyl groups है, these carbonyl groups are going to interact with potassium and they will take away its water molecule. Okay, they will take away its water molecule. तो hydrated potassium ion जो अंदर जा रहा है अभी क्या हो जाएगा? It will just become a dehydrated potassium ion and very easily the potassium will now enter through the pore. So the carbonyl atoms or the carbonyl oxygens, you can say the carbonyl oxygen which is attached to the selectivity filter, they remove the water molecule from the potassium. ठीक है, और वो हाइड्रेटेड वाला फिर आराम से उस पोर के थ्रू चला जाता है. लेकिन जब सोडियम को अंदर जाना होता है, दैट कार्बोनिल ऑक्सीजन्स दे आर नॉट एबल टू इंटरैक्ट विथ सोडियम. सो दीज carbonyl groups or the carbonyl oxygens, they cannot interact with sodium. So because they cannot interact with sodium, this selectivity filter will only allow potassium and it will not allow sodium. So this is how the selectivity is there for the channels for a particular ion. अभी सोडियम का कैसे होता है? सोडियम का जो चैनल है, it is 0.3 into 0.5 nanometers in diameter. Okay, 0.3 to 0.5 nanometers in diameter and it is lined by negatively charged amino acids. Right? So it is lined by negatively charged amino acids. Now these strong negatively charged amino acids, they can pull the small dehydrated sodium ions. Okay, they can pull the small dehydrated sodium ions, but they cannot pull the potassium ions. They were not going to allow the potassium ions to come inside. They will only allow the sodium ions to come inside. So this is the way how there is a selectivity filter for the particular ion, like what they are going to allow. If they are for sodium, only sodium can come inside. If they are for potassium, only potassium can come inside. Now another type of the selectivity which we have made for the channels is what is called as the gating of the channels. Gating of the channels. So the first type of gating of the channels is called as voltage gated channels. Voltage gated channels. इसका मतलब क्या होता है? See, you can see an example. Sodium के voltage gated channels. So this is the closed gate, right? As soon as there is going to be a change in the membrane potential, right? As soon as there is going to be a change in the membrane potential, these channels will open. That means they are able to sense a particular type of voltage. Similarly, potassium channels, they can also sense a particular type of voltage, right? So whenever there is going to be a change in the membrane potential, these channels will open, otherwise they will not open. So this means the voltage over here is acting as a gate. Second wala जो होता है, second wala, they can be ligand gated. Ligand gated. We will see this at the level of neuromuscular junction, that when acetylcholine will bind to its receptors, okay, acetylcholine will bind to its receptors which is present on the muscle side. It will open the ligand gated channels, and those ligand gated channels will then permit the entry of sodium ions. Okay, they will then permit the entry of sodium ions. So sodium ions can be gated through voltage, or sodium ions are also gated through ligand gated channels, where the ligand, what is ligand? It is a hormone or it is a neurotransmitter. So at the level of neuromuscular junction, it is acetylcholine. Then the third important way, okay, the third important way by which is the mechanical gating. Mechanical gating. That means yahan par there is stretch. These channels will open when there is stretch, right? And that stretch or the mechanosensitive channels are especially present in the smooth muscles of blood vessels, or anywhere in the smooth muscles. So whenever the smooth muscles is subjected to stretch, right? Whenever the smooth muscle is subjected to stretch, these channels or these gates will open. And usually these mechanosensitive channels which are opening because of stretch, they usually allow the influx of calcium, because they are especially present in the smooth muscles, right? And the fourth type of channels which you should know are called as the leaky channels. Leaky channels are especially for potassium, and the potassium permeability through the leaky channels can be even 100 times more to potassium as compared to any other ions. So the leaky channels, they permit potassium. Leaky in sense they will allow the potassium to easily come into the ECF or to go out of the ECF. Come into the ICF, or from the ICF it can go to the ECF, and they are not gated. So these leaky channels basically are not gated. That means there is free entry of potassium ions inside or outside, right? So this is how you bring about the channels and the gating of the channels. And you should know this, because once you understand this, then only you will understand the further concepts. And also understand one thing, that see, the sodium concentration is more in the ECF, right? So whenever the sodium channels will open, there will always be sodium influx. Sodium hamesha andar aayega, because the ions, they will always move down their concentration gradient, right? They will move down their concentration gradient. And where is the gradient? Inside. And on the contrary, whenever there is potassium, opening of the potassium channels, the potassium concentrations are more in the ICF. So there is always going to be potassium efflux. मतलब potassium हमेशा बाहर जाएगा, राइट? तो सोडियम का इनफ्लक्स होता है और पोटेशियम का इफ्लक्स. Now let's consider what is our resting membrane potential. So how do you define resting membrane potential? Resting membrane potential is also called as the polarized state of the membrane. That means when it is not stimulated. Polarized state, that means when it is not stimulated. Right? So how do you get this polarized state, or when it is not stimulated? It is defined as the difference between electrical potential. Difference between electrical potential existing on the outside and the inside of the cell. Existing between the outside and inside of the cell at rest. At rest. Right? So at rest bola, that means not stimulated, and that is what is called as polarized. How can you measure? You can measure. What you can do, you can place one electrode. You can place one electrode on the outer surface of cell membrane. On the outer surface of cell membrane, and you will place the another electrode into the interior of the cell. Into the interior of the cell. So one you will keep on the outer surface of the cell membrane, second wala you will keep on the interior of the cell, and you're going to connect the two electrodes to cathode ray oscilloscope. Okay, you're going to connect it to the cathode ray oscilloscope, and you will find, okay, you will find that you are getting your resting membrane potential can be measured. ठीक है? Now under normal conditions the resting membrane potential में कैसे होता है, that the interior is always negative at rest and the exterior is positive. Okay, the interior is negative and the exterior is positive of the resting membrane potential. Now what is the cause of the resting membrane potential is very, very important. That what are the causes of the resting membrane potential, or what are the factors affecting resting membrane potential, or how is there the generation of the resting membrane potential. So the first important thing that should be considered is the concentration gradient across the cell membrane for ions. You basically consider three important ions, that is sodium, potassium and chloride. और इसका बहुत important factor है selective permeability of the membrane. Okay, selective permeability of the membrane. So membrane is not permeable to each and every ion at rest. There is a difference in the permeability. So because there is difference in the permeability, the concentration gradients of the ions, they differ in the ECF and in the ICF. Then you will have to here also know the importance or the role of the sodium potassium pump. Then you have to know about how is the equilibrium potential of each ion generated. This equilibrium potential of each ion is called as Nernst potential. Nernst potential. Then in the case of a membrane, there is no single ion, isn't it? We speak of multiple ions, especially sodium, potassium and chloride. So this is going to be expressed by the Goldman-Hodgkin-Cat equation. Goldman-Hodgkin-Cat's equation. And there is the role of the Gibbs-Donan membrane or Gibbs-Donan equilibrium. Gibbs-Donan equilibrium. So अब आपको जब इसके ऊपर LAQ लिखना है, right? When you are writing an LAQ, over the generation of the resting membrane potential. Remember, all of these factors have to be addressed. आपको लिखना पड़ेगा the selective permeability of the membrane, because of which there is a difference in the concentration gradient of the ions in the ICF and ECF. What is the role of the permeability of the membrane? What is the role of the sodium potassium ATPase? How do the Nernst potential, the Goldman-Hodgkin-Katz equation and the Gibbs-Donan equilibrium, they are all working together and generating your RMP. तो ये सब आपको आना चाहिए. Now if you look into the concentration of these ions, okay, so the concentration of the ions of sodium, potassium and chloride. So how much is there in the ECF and how much is there in the ICF? The values are in milliequivalents per liter. So ECF में sodium is around 150 and 1515 in the ICF, whereas potassium is more in the ICF, around 155 and 4 in the ECF, and chloride is also more in the ECF, that is 110 and around 10 in the ICF, right? तो इससे आपको clear होगा कि what is the movement, right? What is going to be the movement when the channels will open. Now, see, we have seen that there is a cell, and these cells, inside the cells there are proteins. And we know that the proteins are anions. That means they carry negative charge. 1. Second, they are non-diffusible. That means once they are inside, okay, once they are inside, they cannot go outside. So this is contributing to a persistent negativity inside the cell membrane. Okay, it is contributing to the persistent negativity inside the cell membrane. इसकी वजह से क्या हो रहा है कि सेल मेम्ब्रेन अंदर से हमेशा नेगेटिव रहेगी, या सेल अंदर से हमेशा नेगेटिव रहेगा. क्यों रहेगा? क्योंकि there are proteins which are present inside the cell membrane, and these are responsible for the negativity inside the cell, and they will, they will attract positive ions. Because of this negativity, there will be attraction of positive ions and there will be repulsion of the negative ion. So what positive ions can enter? Sodium can also enter, or potassium can also remain inside the cell. दोनों हो सकता है, या तो आप पोटेशियम को बाहर मत जाने दो या फिर आप ज्यादा सोडियम को अंदर लेकर आओ. बट ऐसा नहीं होता है. क्यों? क्योंकि सोडियम आयंस आर नॉट परमेबल एट रेस्ट. नॉट परमेबल भी बोल सकते हैं या डिफ्यूजिबल भी बोल सकते हैं. दे आर नॉट डिफ्यूजिबल एट रेस्ट, right? And even the chloride ions, they cannot move off the cell against the steep concentration gradient. So what will happen? The intracellular negativity will always persist. The intracellular negativity will always persist. So this is the reason that why the resting membrane potential is negative. Why it is negative? Because inside the ions, or sorry, inside the cell, there are proteins which are non-diffusible anions. They can never move out of the cell. और जो थोड़े बहुत chlorides हैं अंदर, even if they are 10 milliequivalents, they cannot move out of the cell against the steep concentration gradient, right? They are also not able to freely move out of the cell because of the steep concentration gradient, and there is no specific chloride pump which is present. जैसे सोडियम के लिए है, सोडियम पोटेशियम पंप है, क्लोराइड के लिए कोई पंप नहीं है. तो इट इज नॉट एबल टू इजीली मूव इनसाइड एंड आउटसाइड एज कंपेयर टू सोडियम एंड पोटेशियम. और सोडियम नॉन डिफ्यूजिबल है, इसीलिए सोडियम को हम बार बार अंदर नहीं लेकर आ सकते हैं एट रेस्ट. सो एट रेस्ट द resting membrane potential will always be negative. Like if you see some values of the neuron, it is minus 70 millivolts. Of the skeletal muscles, it is minus 90 millivolts. Of the cardiac muscles, that means when we speak of the ventricles, it is minus 90 millivolts. But at the level of SA node, it will become less negative. between -55 to -65 millivolts, or smooth muscles are also less negative. उनका RMP is around -40 to -60 millivolts. तो एक बात क्लियर हो चुकी है कि रेस्टिंग मेम्ब्रेन पोटेंशियल हमेशा नेगेटिव रहेगा, राइट? क्यों? क्योंकि proteins are non-diffusible and they are anions and they will always be present inside the cell, right? Now, why there is difference 70, 90? It is because depending upon the tissue, there will be difference in the equilibrium potential of different ions. Okay, depending upon the tissue, there is going to be a difference in the equilibrium potential of different ions. So everywhere the Nernst potential is not same of the ion. It will depend upon, okay, it will depend upon the tissue, and because it is depending upon the tissue, there is going to be a slight variation in the RMP of the different tissues. Now, what is Nernst potential? Right? What is Nernst potential? We will see. Now see over here. You will just elaborate the concept of resting membrane potential thoda sa aur. See, you can see that there are equal number of ions over here. 10 positive, 10 negative, 10 positive, 10 negative. So when the membrane has got equal number of cations and anions, that means when any solution is electrically neutral, there is no resting membrane potential. ठीक है? जब भी there are equal number of ions, positive and negative, and they are balanced, there will be no resting membrane potential. यहाँ पर देखो 15 cations, 10 anions, 5 cations, 10 anions. तो यहाँ पर there is going to be a membrane potential, right? So this is not, these two solutions are not electrically neutral with each other. Even they are not electrically neutral among themselves. यहाँ पर 15 प्लस है और 10 माइनस, यहाँ पे 5 प्लस है और 10 माइनस. So any solution which is not electrically neutral will create a membrane potential. Only that will create a resting membrane potential. Unbalanced ions will create resting membrane potential. Now, over here you see, all these unbalanced ions, they will always be aligned just near the cell membrane. ये देखो, just near the cell membrane. Okay, so जितने ions balanced हैं, they are present here in the solution. But those ions which are not balanced will be accumulated, or they will be aligned just near the cell membrane. Just near the cell membrane. Another interesting thing, A में कितने unbalanced ions हैं? 3. B में 1, 2, 3, 4, 5, 6. और C में 1, 2, 3, 4, 5, 6, 7, 8. That means the magnitude of the resting membrane potential will be maximum in C. More the number of unbalanced ions, more the solution is not electrically neutral, then वहां पर the resting membrane potential का जो magnitude है वो ज्यादा रहेगा, right? So understand what is RMP, the potential difference which is existing with negativity inside. It is always negative because of the non-diffusible anions, that is proteins, which will never move out. The magnitude of the RMP will depend upon the total number of ions which are unbalanced, because जो balanced है, they are quite settled in the solution. जो unbalanced है, they are going to be aligned across the cell membrane, right? So you must remember that unbalanced वाले जो है, और वो जितने ज़्यादा होंगे, उतना magnitude of the RMP will be more. Now, what is Nernst potential? Nernst potential, which is also called as the equilibrium potential, also called as the diffusion potential, because it is because of the diffusion of the ions. What is the cause? Diffusion of the ions, and therefore it is also called as diffusion potential. So let's consider one by one. Okay, now let's consider that there is a membrane which is only permeable to potassium. Ab potassium concentration, we know it is more inside, so potassium ions will move outside, right? The potassium ions will move outside. So because the concentration of the potassium is more on the inside, the potassium ions will move outside. This is called as concentration gradient. So because of the concentration gradient, ठीक है, because of the concentration gradient, the potassium ions are moving to the outside. Now, once the potassium ions start moving to the outside, what happens? The inside negativity increases because अंदर तो बहुत सारे anions हैं, है ना? तो अंदर anions बढ़ गए हैं. So what will happen? The potassium which are going or which went outside to the ECF will come inside. वो वापस से अंदर आ जाएंगे to neutralize the negativity. So when the potassium ions are coming from outside to inside because of the negativity, this is called as electrical gradient. Okay, it is called as electrical gradient. So potassium ions बाहर जा रहे हैं because of concentration gradient. Potassium ions अंदर आ रहे हैं because of electrical gradient. Now there will be a particular potential at which there is no net diffusion of ions. No net diffusion of ions. So that point where there is no net diffusion of ions, that means they are equally balanced or there is no movement of ions, is called as the equilibrium potential or the Nernst potential for potassium, right? So the electrical potential that counters the net diffusion of the potassium ions is called as the equilibrium potential. So that potential at which there is no net movement of the potassium ions is called as the equilibrium potential. How can you calculate? I'll tell you. So remember that if you look into the permeability, potassium ka permeability is more than chloride, which is more than sodium. The Nernst potential when we calculate for potassium is between -90 to -94, sodium +61 to +65, chloride -70 to -65. Also remember that the sodium channels can be blocked by tetradotoxin and the potassium channels can be blocked by tetraethyl ammonium. These come as MCQs, so this you should know. So यहाँ पर एक बात रखना, most diffusible ion at rest and the ion with maximum contribution to RMP, दोनों का आंसर रहेगा potassium. Okay, the ion with maximum contribution to RMP or the ion which is most diffusible at rest, दोनों का आंसर रहेगा potassium. So the Nernst potential can be mathematically calculated as, for example, यहाँ पर हम लोगों ने chloride का लिया. The equilibrium potential is equal to RT divided by FZ. Okay, and chloride concentration outside by inside. Chloride concentration outside by inside, where R is the gas constant, T is the absolute temperature, F is the Faraday's number, and Z is the valency of the chloride ions. Now what we will do, we will just convert the natural log to the log base 10. Okay, once we convert the natural log to the log base 10 and we replace the constants, the gas constant and the absolute temperature, simply we can see that the chloride equilibrium potential can be calculated as 61.5 log concentration of sodium inside upon concentration of sodium outside. So ऐसे ही हम लोग बाकी का भी calculate कर सकते हैं. So equilibrium potential for sodium will be 61.5 log concentration of sodium inside by outside. This is how we calculate the Nernst potential. So the first step in calculating the resting membrane potential would be calculation of the Nernst potential for each ion. So we can calculate the Nernst potential of each ion. अगर यही हम लोग सोडियम की बात करेंगे, सोडियम का concentration कहाँ है ज़्यादा? ECF में. So it will always have a tendency to come inside. Okay, inside. So this is called as the concentration gradient. And why it always wants to come inside? Because the inside is negative and sodium is a positive ion. That means in the case of sodium, the electrical gradient and the concentration gradient both are in the same direction, that is towards inside, right? Both of them are towards inside. And क्लोराइड का कैसे होता है? क्लोराइड का कॉन्सेंट्रेशन ज्यादा कहां पर है, right? Where is the chloride concentration more? Chloride concentration is more in the in the ECF, right? So it will also try to come inside. But remember that chloride में कैसे होता है? It has no specific chloride pump, as you have got specifically for sodium and potassium. So there is no specific chloride pump, and therefore it has got no active influence, on RMP. It is just passively distributed on the two sides of the cell membrane. Just passively distributed on two sides of cell membrane in accordance with the RMP. Okay, in accordance with the RMP. Now, so this is how we calculate the Nernst potential for each ion. Now, when we consider our cell membrane is not permeable or not only acted upon by one single ion. We have got three ions which are working: sodium, potassium and chloride. So the Goldman-Hodgkin-Katz equation takes into consideration two important things. It not only takes into consideration the concentration of the ions, okay, concentration of the ions, but it also takes into account the permeability, okay, the permeability of the ions. So यहाँ पर the P stands for permeability, okay, और bracket के अंदर जो है that is concentration. The bracket indicates the concentration. This bracket, okay, this bracket indicates the concentration. And I is inside and O is outside. Okay, I is inside and O is outside. Now, so you can see that Vm, that is the membrane potential, is permeability of potassium into concentration of potassium outside divided by permeability of potassium into concentration of potassium inside, plus permeability of potassium and concentration of potassium outside divided by permeability of sodium and concentration of sodium inside, plus permeability of chloride in and concentration of sodium inside divided by permeability of chloride and concentration outside. So you can see that just to maintain the electrical neutrality of the equation, when we consider the two positive ions, okay, when we consider the two positive ions, that is potassium and sodium, and we take outside by inside, chloride का हम लोग लेंगे inside by outside, just to maintain the electrical neutrality. Similarly, if you have taken potassium inside by outside, sodium inside by outside, chloride का आप लेंगे outside by inside, right? Chloride का आप लेंगे outside by inside. So just to maintain the electrical neutrality, you are reversing the direction of chloride ions. So when you are calculating your resting membrane potential with the help of the Nernst potential and with the Goldman-Hodgkin-Katz equation, ये दोनों की मदद से when you are calculating the resting membrane potential, the value comes minus 86 millivolt and the remaining minus 4 millivolt is contributed by your sodium potassium ATPase pump. Okay, so Nernst potential से और Goldman-Hodgkin-Katz equation से when you are calculating the resting membrane potential, it comes minus 86 and minus 4 is contributed by the sodium potassium ATPase pump. Now again I told you that the Nernst potential is different of the ions at different tissues, and this is the reason that why the resting membrane potential is different at different tissues, like 55 in the smooth muscles but 90 in the skeletal, 90 in the cardiac. So it is mainly because the RMP differs because of the difference in the equilibrium potential of the ions. तो ये ध्यान में रखेंगे. अब इस इक्वेशन से हमको बहुत ज्यादा इंपॉर्टेंट बात पता चलती है, वो ये है कि कॉन्सेंट्रेशन तो कोई भी आयन का इंपॉर्टेंट है, राइट? कॉन्सेंट्रेशन तो कोई भी आयन का इंपॉर्टेंट है, लेकिन उससे ज्यादा इंपॉर्टेंट होता है उसका परमिएबिलिटी. सो जिस आयन की परमिएबिलिटी ज्यादा होगी, आई रिपीट, जिस आयन की परमिएबिलिटी ज्यादा होगी, दैट आयन इज गोइंग टू कंट्रीब्यूट मैक्सिमम, that ion is going to contribute maximum to your resting membrane potential. And when we speak of permeability, the ion which is most diffusible at rest, the ion which is most diffusible at rest is potassium, because the potassium permeability is far more as compared to chloride or to sodium, right? So Goldman-Hodgkin equation also gives us the significance of the permeability of the ion and not only the concentration gradient. So all the ions, let it be sodium, potassium or chloride, they want that their equilibrium potential, okay, they want that their equilibrium potential should be closest to the RMP. हर कोई दौड़ रहा है और चाह रहा है कि हमारा जो equilibrium potential है या हमारा जो Nernst potential है, that should be equal to the RMP. बट आरएमपी का सबसे क्लोज किसका जा रहा है? पोटेशियम का. द नियरेस्ट और द मैक्सिमम कंट्रीब्यूशन टू आरएमपी इज बाय द पोटेशियम, और द इक्विलिब्रियम पोटेंशियल ऑफ द पोटेशियम इज नियरेस्ट टू आरएमपी. व्हाट इज द रीजन? द रीजन इज मैक्सिमम परमिएबिलिटी ऑफ द पोटेशियम आयंस इवन एट रेस्ट, राइट? Now remember that the sodium potassium ions, they are contributing only to -4 millivolts. ज़्यादा contribute नहीं कर पा रहे हैं वो. Okay, the contribution is only -4, but the sodium potassium pump plays a pivotal or a very important, a pivotal role in establishing or maintaining the concentration gradients, in maintaining the concentration gradients of sodium and potassium across the cell membrane. Though it is not very much contributing, सिर्फ -4 millivolt का ही contribution है, लेकिन उसका सबसे ज्यादा importance आ रहा है, वो concentration of ions को maintain कर रहा है, sodium और potassium. So अगर आपने कोई drug दी, okay, कोई drug दी that blocks the sodium potassium pump. So what will happen if the sodium potassium pump is blocked? You will see that the resting membrane potential will slowly disappear. It will slowly disappear. What is the reason? If the sodium potassium pump fails, you won't be able to maintain the concentration gradients of sodium and potassium across the cell membrane. That is more sodium outside and less and more potassium inside. So this maintenance, or very, very importantly, re-establishing the RMP after action potential. Action potential होने के बाद, when there is re-establishing, that is done mainly by the sodium potassium pump. So if the pump fails, what will happen? You will actually lose the resting membrane potential. Now the last factor which contributes indirectly is the Gibbs-Donan equilibrium. Now what is this Gibbs-Donan equilibrium? Okay, इसको देखते हैं अभी कि what is the Gibbs-Donan equilibrium. Now when there are two solutions which are, when there are two solutions, okay, they contain various ions and they are separated by a semi-permeable membrane, okay, by a membrane. And what is the problem? That this membrane is permeable to certain ions, it is permeable to certain ions and it is impermeable to some other anions, cations or to some other solutes or other substances. So ऐसा कुछ हो रहा है कि एक membrane है which is permeable to certain ions and some which is not permeable to certain ions. That means mathematically you are not having electrically neutral solution, but still you are trying to maintain a equilibrium. Then there is going to be a role of Gibbs-Donan membrane equilibrium. So there are certain diffusible cations and anions at rest. There are certain diffusible cations and anions at rest, but there is also distribution of or presence of some non-diffusible anions on one side. At that time, mathematically what you are obtaining the equilibrium, okay, mathematically what you are obtaining the equilibrium is called as the Gibbs-Donan membrane equilibrium. ठीक है, तो mathematically we have seen that this is a solution which contains sodium chloride on each side, and on the solution A there is an anion which is X. Okay, so how is going to be the equilibrium over here, and then we will see कि हमारे body में कैसे होता है. So each solution is supposed to be electrically neutral, that is the cations A and the anions A and the cations B are equal to the anions on the B, right? So the sodium concentration on A is equal to the chloride concentration on the A, and similarly the sodium concentration on the B is equal to the chloride concentration on the B. So both solutions are electrically neutral. Suppose 5, 5, 5, 5. So there are equal number of cations and anions on either side and they are well settled. So the product of diffusible ions on both sides, sodium on A side multiplied by chloride on A side is equal to sodium on B side multiplied by chloride on B side. So how do you obtain the ratio of this? Diffusible cations on A side divided by diffusible cations on B side is equal to diffusible anions on B side divided by diffusible anions on A side. Right? So this is what you are getting. Sodium on A divided by sodium on B is equal to chloride on B divided by chloride on A. Now this is possible when the solution is electrically neutral. Now what will happen if the solution is not electrically neutral? Then what you will do? Now suppose you add an anion. This is anion X, and suppose this is non-diffusible. Now what will occur? अब आप कैसे करोगे? Suppose initially there were 5, 5, 5 and 5. Now you've added 2 anions. So अभी cations हो गए 5 और anions हो गए 7. Now how will you bring about the electrically neutral solution? अब आपको क्या करना पड़ेगा? X तो already non-diffusible है, इसलिए X का तो कुछ भी नहीं हो सकता है. X is non-diffusible, it cannot move out. तो आप क्या करेंगे? इसमें से जो एक्स्ट्रा क्लोराइड आयंस हैं जो कि डिफ्यूजिबल है, इसको आप बाहर भेज देंगे. कितने एक्स्ट्रा हो गए? हमें सिर्फ 5 केटायन चाहिए और हमारे पास सिर्फ 5 केटायंस हैं. हमको सिर्फ 5 एनायंस चाहिए, तो हम इसके जो 2 हैं, क्लोराइड के जो 2 हैं, इसको बाहर भेज देंगे. ओके, दैट मीन्स क्लोराइड नाउ हियर विल बिकम 3. सो 3 क्लोराइड हो जाएंगे, 2 प्रोटीन्स हो जाएंगे. तो अभी हमारा सोल्यूशन बन जाएगा इलेक्ट्रिकली न्यूट्रल. 5 एनायंस एंड 5 केटायंस. गॉट दिस पॉइंट? This is a condition which is exactly taking place in the body. See, now you will understand. This is my ICF and this is my ECF. So initially I have got potassium over here, sodium chloride over here, and I've added the anions, that is proteins, and now that the proteins are non-diffusible and they are anions. So what will happen? The chloride which is present here have to go outside, isn't it? The chloride which is present on the ICF has to move outside because the chloride is negatively charged. It is going to be repelled by the proteins. Okay, it is going to be repelled by the proteins, and therefore the chloride has to move outside. So that is the reason, because of this Gibbs-Donan effect, you will see that the chloride concentration is more in the ECF. Why? The chlorides want to remain inside, but they cannot remain inside because they are repelled by already existing proteins. Now, this is the reason that why there is favorable diffusion for potassium, and the potassium concentration is more inside. So because you have got anions inside, there is always a tendency that the positive ions will come inside, right? There is always a tendency that the positive ions can come inside. The only positive ion which can come inside at rest is potassium. क्यों? क्योंकि potassium ही maximum diffusible है. So the Gibbs-Donan equilibrium is indirectly contributing to the movement of potassium from outside to inside. Potassium favors coming inside, and it is again facilitated by the Gibbs-Donan effect, because the Gibbs-Donan effect helps to tell us that the proteins, they cannot move outside, so you have to get in the negative ions, and the only negative so you have to get in the positive ion, and the only positive ion which can enter inside at rest is potassium. So Gibbs-Donan equilibrium के वजह से the potassium concentration is more in the inside and the chloride concentration is more on the outside. This is one of the important factor of the Gibbs-Donan equilibrium, right? Now remember that in the body it plays an important role. How? So because of this, remember that in the body, its significance is that we have got non-diffusible proteins inside this cell. We have got non-diffusible proteins inside the cell, right? Now, because of this fact, yesterday also I have told you in osmosis that the cell has more amount of osmotic particles. Right? The cell has got more amount of osmotic particles, and there is a tendency that the cells can swell, right? But we are thankful to the sodium potassium ATPase pump that it is going to extrude or pump the extra amount of sodium to outside. It will not allow more osmotically active particles to get accumulated, है ना? तो अगर सोडियम ज्यादा अंदर आ गया, बिकॉज सोडियम इज वेरी वेरी स्ट्रॉन्ग ऑस्मोटिक इफेक्ट क्रिएटिंग एजेंट, जहां पे भी सोडियम ज्यादा होगा पानी विल कम इनसाइड, राइट? सो इनफैक्ट क्लोराइड्स को भी वो अट्रैक्ट करता है. So remember that sodium potassium pump is playing a very very important role because it is throwing the extra sodium outside, and therefore if the sodium potassium pump fails, the cells will swell and they will burst, right? So remember, one is the important role of this Gibbs-Donan equilibrium. Second is because of the non-equal or because of the unequal distribution. There is unequal distribution of cations and anions. There is unequal distribution of cations and anions at equilibrium. An electrical potential difference is generated. An electrical potential difference across the cell membrane is generated in accordance with the Nernst equation. Okay, in accordance with the Nernst equation. That means some amount of contribution of the Donan effect is to your RMP, right? It is there to the RMP. Now next. So finally remember that RMP is always going to be negative, right? Because of the presence of the non-diffusible anions, that is proteins. It is always going to be negative. And when I have to write an LAQ over RMP, I will have to elaborate all of this. First, what is the cause of negative RMP? Second, always mention about the selective permeability of the membrane, because this selective permeability of the membrane is responsible to develop the concentration gradient of ions across the cell membrane. ये आपको mention करना पड़ेगा. Then you will have to write about the Nernst potential and the Goldman-Hodgkin-Katz equation, which are contributing to minus 86 millivolts of RMP. Then the sodium potassium pump, which is contributing to minus 4 millivolts of RMP, and how the Gibbs-Donan effect is indirectly contributing to generation of RMP. तो इतना पूरा अगर आपने लिखा तो आपका आंसर कंप्लीट हो जाता है if it is an LAQ. और अगर ये शॉर्ट नोट है, if it is just a short note, then just mention that these are the causes, right? Now we next on move to another very important topic, that is our action potential, right? So if there is any doubt up till now, अगर कोई भी doubt है तो उसको आप पूछ सकते हैं, so that you can really understand well. If there is any garbad, so you can really understand well if there is anything which is to be cleared. Or you can, whenever you are watching, you can put, so that I can complete the question or the query in the next class. Now, this is action potential. So this is a very, very important, image-based question also in the NEET UG as well as in the NEET PG. में बहुत important आपका NEET PG question है. So very common answer which will be, or the question is, what is the cause of the upstroke, or which ion is responsible from the phase B to D, right? Which ion is responsible from the phase D to E? What is F called as? What is the cause of F? Okay, तो ऐसे ऐसे जो causes हैं, that means they are totally dependent upon the ionic basis of RMP, right? So जब भी हम लोगों को ionic basis of action potential, हम लोगों को जब भी कोई question आता है which is related to the image, always consider two important things. See, ऐसे, so तीनों ही action potential है. Now this is minus 90, this is suppose minus 90, this is minus 55, right? Or I may even draw like this, and this is minus 40. So you must always look over to the shape of the action potential. Like this is a plateau, this is also a plateau, this is called as spike, this is also called as spike. So आपको क्या देखना चाहिए? सबसे पहले आपको देखना चाहिए कि उसका शेप क्या है, स्पाइक है या प्लेटो, और फिर आपको देखना चाहिए उसका RMP कितना है. So plateau and RMP 90 cardiac muscle, plateau and RMP 40 smooth muscle, spike minus 90 skeletal muscle, spike minus 55 pacemaker potential, that is the potential of the SA node, right? So always concentrate on the shape of the action potential and the resting membrane potential, right? Now, how do you define action potential? In the exams, this is also a viva question. Define RMP, define action potential. ये simple viva questions है जो हम लोगों को आते ही नहीं. I don't know why don't are we able to define it. Definition is the thing which is the first thing which we should know. So what is the definition of action potential? It is defined as the sequential change in the membrane potential. It is defined as the sequential change in the membrane potential due to opening or closure, of ion channels, opening or closure of ion channels and its propagation along the excitable tissue and its propagation along the excitable tissue. This propagation along the excitable tissue which is non-decremental. Non-decremental. That means once it develops a particular magnitude or a particular intensity, it is going to travel with that same intensity throughout the membrane, right? So definition is the sequential change in the membrane potential due to opening or closure of the ion channels and its propagation along the excitable tissue which is non-decremental. What is the use of action potential? Anybody? Why action potential is important in our body? See, body is made up of nerves, right? Body is made up of nerves, kind of wires. And for any impulse to be transmitted, you have to convert it into an action potential. And that is the basic role of cell receptors also. The receptors, they behave as transducers and they convert any form of energy into electrical energy, because these membrane potentials will then bring about their effect. Their effect could be either muscle contraction, their effect could be either release of a neurotransmitter, right? They have to release some vesicles, or even a reflex response, moving your hand away, even a reflex. Everything in our body is brought about with the help of action potentials, right? So I'll draw first and then we will understand the phases. Once we understand the phases, then we will understand the ionic bases. Okay, so every phase has got importance. And the potential at which that phase is occurring is also very, very important. Right? So now if I write resting membrane potential of minus 70 millivolts and it is a spike, so you must remember that it is the action potential of neuron, right? Then it is very, very important, you know, to have the significance of these voltages. Minus 55 millivolts, then 0 आना चाहिए, and this spike per there is plus 35 millivolts, right? This much if you draw is sufficient, quite sufficient. Now let's write this first. Let us, you know, first know the phases, and once we know the phases, we will study the causes or the ionic bases. Now, as we know that at resting membrane potential, okay, that means when it is not stimulated, which we also call as the polarized state, the membrane from the inside is negatively charged. Inside is negatively charged and outside is positive. Okay, inside is negatively charged and outside is positive, and this stage of RMP is called as polarized. You have to know these terms. इसको ऐसे लिखना ही पड़ता है हमको. It is called as polarized, right? Now what happens that with the onset of action potential, the polarity would be reversed. With the onset of action potential, the polarity would be reversed. That means what will happen? The inner surface will become positive. Once the inner surface becomes positive, then later on it will now again gradually it will become negative. Okay, so once it is becoming positive, once the inner surfaces become positive ऊपर जा रहा है, this stage is called as depolarization. This is called as depolarization. And subsequently, once it becomes positive, उसके बाद वापस it is starting to become negative. That means it is becoming negative का मतलब क्या होता है? It is becoming negative का मतलब होता है you are actually bringing about the recovery of the polarized state. You are actually bringing about the recovery of the polarized state. It is very important that once the membrane becomes positive, it should again become negative from inside. If it does not become negative from inside, it is not going to generate the next action potential. So it is very important कि वो जैसी positive हुआ depolarize, it should recover and it will move towards its negativity. So once it comes to its negativity, that phase will be again called as repolarization. So you have got two important phases, that is depolarization and repolarization. And again, with the help of the cathode ray oscilloscope, CRO, you can measure the action potential. Now let's consider each and every phase nicely. So first, this is the point where you gave a stimulus. Okay, this is the point where you gave a stimulus and this is the point of firing level. इसको अलग ड्रॉ कर देते हैं. यहाँ से हमारा चालू हुआ है firing level. Right? So ये जो थोड़ा सा एरिया बचेगा, this much will be our latent period. Okay, this will be our latent period. Now I'll make you understand and then I'll start writing. ऐसे आपको समझेगा नहीं. Now, as soon as you give a stimulus, what will happen? Once you give a stimulus, there is going to be a leakage of current. There is going to be a leakage of current from the stimulating electrode to the recording electrode. Leakage of current from the stimulating electrode to the recording electrode. This is resulting, or what is this small leakage of current is what is called as stimulus artifact. This is called as stimulus artifact. So जैसे आपने threshold stimulus दिया, there is small amount of leakage of current, okay, from the stimulation from the leakage of current from the stimulating electrode to the recording electrode, that is producing a small spike जैसा छोटा सा, that is called as stimulus artifact. And it is very important because वहां पर आपको actually क्या पता चल रहा है? आपको पता चलता है टाइम ऑफ एप्लीकेशन ऑफ स्टिमुलस. आपको पता चलता है टाइम ऑफ एप्लीकेशन ऑफ द स्टिमुलस. इसके बाद में देयर इज अ शॉर्ट इंटरवल बिफोर द डीपोलराइजेशन बिगिंस. ओके, अ शॉर्ट इंटरवल बिफोर द डीपोलराइजेशन बिगिंस. And that short interval before the depolarization begins is called as your latent period. So it is actually the time that is required. यहाँ पर क्या होता है? The time that is required from for the electrical impulse to pass from the stimulating electrode to the recording electrode. Okay, so it is the time that is taken by the electrical impulse. The time that is taken by the electrical impulse to pass from the stimulating electrode to the recording electrode. That means it is proportionate to the distance between the stimulating electrode and the recording electrode, and it also depends or is inversely proportional to the velocity of impulse conduction. अगर आपको याद होगा तो आपने प्रैक्टिकल भी किया होगा ना, फर्स्ट एमबीबीएस में आपको एक ग्राफ है जिसमें आपको दो ग्राफ है, मसल एंड, नर्व एंड, और उसको हम लोग बोलते हैं दैट इज द ग्राफ दैट इज बेस्ड अपॉन द कंडक्शन वेलोसिटी ऑफ नर्व फाइबर. ओके, कंडक्शन वेलोसिटी ऑफ द नर्व फाइबर का ग्राफ है. सो दिस इज द stimulus artifact, then that is the latent period. Now at the end of latent period, when the muscle will start becoming positive, now this is very important to understand. I'll write and then I'll again make you understand. You will see that as the latent period ends, and you say now that there's going to be beginning of depolarization. Okay, there is beginning of depolarization. Remember the first 7 millivolts, okay, जो पहले का नेगेटिविटी थोड़ा सा कम हो रहा है, सपोज -70 से 7 millivolts नेगेटिविटी कम हो जा रही है, the first beginning or the first 7 millivolt is just because of the passive movement or the passive, this is entirely passive, is entirely passive. It is just because of the electrotonic changes. What do you mean by electrotonic changes? Just because of the passive movement of the charges. When you are giving a stimulus, there is just a passive movement of the charges. There is no active participation of the channels, and therefore it is entirely passive and is called as just because of electrotonic changes. So the first 7 millivolts will not decide that whether the action potential is going to be depolarizing or not. Now when the depolarization changes from 7 to 15 millivolts, this is called as actually the threshold for excitation. Okay, threshold for excitation after this. So from the 7 to the 15 millivolts, you will see that there is opening of the sodium channels and there will be influx of sodium. लेकिन अभी भी influx of sodium is not so massive so as to overcome the exit of potassium and entry of chloride. ठीक है, तो रिमेंबर जब आपने एक स्टिमुलस दिया तो पहले तो जस्ट देयर इज अ पैसिव लीकेज of the ions that is contributing to only a change of 7 millivolts. फिर 7 से लेके 15 millivolts तक भी सोडियम चैनल्स खुल जाते हैं और सोडियम अंदर आना स्टार्ट हो जाएगा, लेकिन इतना सारा सोडियम अंदर नहीं आ पाएगा. अभी भी देयर इज अ बैलेंस बिटवीन द सोडियम इनफ्लक्स एंड द पोटेशियम इफ्लक्स एंड द क्लोराइड इनफ्लक्स. ये सब कुछ हो ही रहा है, बट एट दिस स्टेज if the depolarizing forces they go higher, okay, that means at -55 millivolts, which is the threshold for excitation, this is the stage which is actually resulting in the opening of more and more of sodium channels. There is a massive opening of the sodium channels and the sodium influx will be so rapid and so massive that it is going to result in simultaneous entry of so many sodium ions, and that is going to go up, that is cross the O0 level, that is also called as overshoot, and become a positive upstroke or a depolarizing effect. See, so initially when you give a stimulus and there is a latent period, so initial first 7 millivolt of changes, मान लीजिए यहाँ तक, they are of not much significant importance. There is no active participation of the sodium channels, just a leakage of small amount of sodium. Then from 7 to 15 millivolts, यहाँ तक भी although the sodium ions have started coming inside, but still they are counterbalanced because the potassium is moving out and the chloride is also coming in. Once this -15 reaches to -55, which is a point of threshold of excitation, nobody can now stop the upstroke. Okay, nobody can now stop the upstroke, because what will happen, there is a kind of a positive feedback mechanism, the Hodgkin cycle of opening of the sodium channels. That opening of the few sodium channels will result in opening of more and more and more of the sodium ions, sodium channels, to an extent that sodium will now come inside. It will cross this zero, which is called as overshoot. It will cross the zero, which is called as overshoot, and it will result in this spike of plus 35 millivolts, right? So if at plus 35 millivolt, if you do not allow the sodium channels to close, what will happen? The sodium channels will remain open. The sodium ions will keep coming inside, inside up to plus 65 millivolt, which is the Nernst potential for sodium ions. So I repeat, अगर आपने प्लस 35 पर सोडियम चैनल्स को क्लोज नहीं किया और सोडियम चैनल्स आपके खुले रह जाते हैं, तो सोडियम इनफ्लक्स कंटिन्यूसली होता जाएगा जब तक मेम्ब्रेन सोडियम का नर्न्स पोटेंशियल को अराइव नहीं कर लेती, विच इज प्लस 65. बट वी आर नॉट अलाउइंग दैट. द रीजन फॉर दिस इज the sodium channels which are voltage gated, they are very fast to open but they are fast to close. So as you reach at plus 35, at this point the sodium channels will close and the potassium channels will open. So at plus 35 millivolts, which is the spike potential, what will happen? The sodium channels will now close and the potassium channels will now open. Remember, these are fast voltage gated channels and these are slow voltage gated channels. Sodium channels, they open fast and they close fast, but the potassium channels, they are slow to open and they are slow to close also. So the initial, once the spike potential is reached, the sodium will be, the sodium channels can now will now close because they can sense the voltage. Actually they are voltage gated, so they will sense the voltage and they will close and the potassium will open. So once the potassium channels will open, what will happen is that there will be efflux of potassium, right? There will be efflux of potassium, and now the sodium is not going to come inside anymore, but there's going to be efflux of potassium. So this efflux of the potassium will again cause the cell interior to become negative. Okay, it will again cause the cell interior to become negative, and this is going to result in your downstroke. Now remember, the initial part of the repolarization is very rapid. The initial part of the repolarization is very rapid, but thoda sa part is bit slow. The last part of the repolarization is slow, which is also called as after depolarization. Okay, so this is your repolarization, and the initial part of the repolarization or the downstroke is very rapid, and the last part or the later wala part, which is called as after depolarization, is slow. Right? Now what do we get over here is after hyperpolarization. After hyperpolarization, that means the resting membrane potential is becoming more negative than the RMP. The cause of this is the continued efflux of the potassium ions. Okay, the continued efflux of the potassium ions. Remember, the potassium channels, I told you that they are slow to open and they are slow to close. Right? They are slow to open and they are slow to close. So because they are slow to close, there is a continued efflux of the potassium ions that causes the resting membrane potential to become more negative, right? More negative, and that is called as after hyperpolarization. It is called as after hyperpolarization. Okay? So stimulus artifact, just leakage of ions, latent period, okay, up to -7 millivolts. There is no active participation. From 7 to 15, opening of few sodium channels, but not very consistent to cause upstroke, because even at that time we will see that there is continued सोडियम इनफ्लक्स, बट पोटेशियम का भी इफ्लक्स हो रहा है और क्लोराइड भी अंदर आ रहे हैं. बट वंस it reaches up to -55, this is called as threshold for excitation, resulting in the massive explosive opening of sodium channels. Large amount of sodium ions, they come inside and result in upstroke, extreme positivity. It crosses the overshoot, that is 0, and reaches up to plus 35. At plus 35, the sodium channels will close and the potassium channels will open, resulting in the downstroke. That means now taking the polarity back towards its original. That means cell interior should be again negative. The first part of the repolarization is rapid. The later part of the repolarization is bit slow, which is called as after depolarization. Because of the slow continued efflux of potassium, what you get is more negative RMP. This more negative RMP is called as after hyperpolarization. Eventually, the resting membrane potential will be established. Now, the re-establishment of the resting membrane potential is the role of the sodium-potassium pump. It will take care that if there is any extra amount of sodium which is present inside, it should be pumped outside, and the potassium which are outside should be brought back inside, so that you can re-establish the concentrations of sodium and potassium. So सोडियम पोटेशियम पंप का बहुत बड़ा इंपॉर्टेंट रोल होता है इन री-एस्टैब्लिशिंग द रेस्टिंग मेम्ब्रेन पोटेंशियल, बिकॉज इफ यू डू नॉट री-एस्टैब्लिश यू कैन नॉट क्रिएट द नेक्स्ट एक्शन पोटेंशियल. ओके, नाउ so remember, ionic basis is LAQ. Now see over, you can see over here, it's a beautiful diagram, it's very nice. Now basically, you know, when you give a stimulus, okay, what is a stimulus? There is going to be a change in the membrane potential. So you will open sodium channel, chloride channel, potassium channel, but that particular potential is going to be favorable only to one ion, सबको नहीं. सो देखो ये वाला जो ग्राफ है फर्स्ट टॉप वाला, ये एक्शन पोटेंशियल है. सो दिस इज द अपस्ट्रोक ऑफ एक्शन पोटेंशियल. You can see that in the upstroke of action potential, the conductance of sodium is maximum, right? The conductance of sodium is maximum. Whereas जैसे हम प्लस 35 पर आ गए तो सोडियम का कंडक्टेंस कम होते जा रहा है, because the channels are closed. And once you reach this spike, that means just the point where the sodium channels are closing, that will be the point where the potassium conductance will increase, and it will continue to increase till after hyperpolarization. So after hyperpolarization is because of the continued so slow efflux of the potassium, and RMP is again by your sodium potassium pump. I hope it is very clear now, because this topic is very, very important, right? Now, so we've already seen how the factors they contribute to action potential. So we've seen the role of sodium potassium pump. After termination of the action potential, the membrane will re-establish its original state, but abhi bhi there is a small amount of disequilibrium, because the sodium channels they close very fast. So abhi bhi aap dekhenge ki sodium is more inside and the potassium is more outside. Now if you want that the next action potential should be developed, okay, so the next action potential can be attained only if you re-establish, and that re-establish or the ionic balance का जो restore है, that is brought about by sodium potassium pump. Now role of chloride ions. Remember, chloride ions usually have got no role. Chloride ions have no role in action potential, because there is no change in the membrane permeability to the chloride ions in resting condition. Moreover, the chloride channels are not voltage gated. Okay, there is simply a kind of leakiness, or there is simply a passive diffusion of these ions. So the chloride ions are not responsible for RMP directly, and also they are not opening or closing with the action potential. There is only a passive diffusion. Now, what is the role of calcium ions? This is very, very important, and this is also asked in your Viva. Very important. See, you know that the calcium ions, they are important for the muscle contraction. But whenever there is hypocalcemia, okay, whenever there is hypocalcemia, again you see that there is increase in the neuromuscular irritability. That means you get muscle spasm. You will find essay carpopedal spasm with hypoparathyroidism. What is the reason? The reason is that calcium ions basically stabilize the sodium channels. They stabilize the sodium channels, or they kind of gate the sodium channels. They do not allow the sodium channels to open at any voltage. But whenever there is a decrease in the calcium concentration, the voltage gated sodium channels destabilize. The voltage gated sodium channels, they are destabilized. And what will happen? They will start opening. They will start opening even with subthreshold stimuli. Even if there is a small change in the membrane potential, they will open and result in this neuromuscular irritability, paresthesias, or the muscle spasm. So calcium ions directly कोई role नहीं है, but calcium ions, they gate the sodium channels so that the sodium channels do not open abruptly. So whenever there is hypocalcemia, right, whenever there is hypocalcemia, what will happen? That the sodium channels will open even if there is a small change in the membrane potential, and they will result in entry of the small amount of sodium, which will cause excitability of the membrane and features like paresthesias or muscle spasm. And this is asked in Viva also. तो इसको थोड़ा सा ध्यान में रखेंगे हम लोग. ठीक है? Now see. अभी देखो. These are acute subthreshold potentials, and this is action potential. So this is the basic difference between what we called as a local response, which are the graded potentials, also called as the local potentials. So what did I tell you? I told you that unless and until a membrane reaches minus 55 millivolts, okay, unless and until the membrane reaches minus 55 millivolts, which is called as threshold of action potential, it cannot generate the upstroke. It cannot generate the sufficient upstroke or the depolarization. उसके पहले जो ये छोटे छोटे आपको potentials मिलते हैं, these are all local potentials, and these local potentials can be brought about just even by a subthreshold stimuli, because they are not able to reach the voltage up to minus 55 millivolts, right? Unless and until these local potentials, they reach up to minus 55 millivolts, only then the local potential will be converted into an action potential. Otherwise ये ऐसे ही रहेंगे, local subthreshold potentials रहेंगे ये लोग. ठीक है? So what are the basic differences between the action potential and the graded potentials? ये आता है आपको. Action potentials can be brought about only by threshold or a supra-threshold stimuli, never by subthreshold. Graded potentials can be brought about by a subthreshold stimuli, right? Action potentials are self-propagatory. That means once they start, they are going to travel the entire membrane, right? And they are non-decremental. Non-decremental का मतलब क्या होता है? The magnitude will not decrease. Suppose this is the magnitude. They are going to travel with the same magnitude. ये जो होते हैं, दे आर नॉन सेल्फ प्रोपगेटरी, दे कैन डाई एनी टाइम, दे आर नॉन सेल्फ प्रोपगेटरी, and they are decremental, that means their magnitude can decrease. Action potentials by and large are always depolarizing, but gradeds can be depolarizing, they can also be hyperpolarizing. Action potentials always produce a response, they have got some effect, always they produce a response. मतलब कोई तो इफेक्ट आएगा, मसल कॉन्ट्रैक्शन है या कुछ सिक्रीशन है, इसमें नॉट नेसेसरी, they may or they may not produce, right? Action potentials, they show all or none law, they do not obey all or none law. Action potentials do not show summation. But these, because they are brought about by the subthreshold stimuli, they show or they exhibit summation, right? They show or they exhibit summation. So ये short note जैसा भी आता है, difference between the local and the action. तो यहाँ पर अगर आप मुझसे पूछोगे कि मैम एग्जाम्पल्स बताओ ग्रेडेड पोटेंशियल के, तो हम लोग तो पढ़ेंगे ना बाद में, बट फॉर नाउ यू मस्ट रिमेंबर रिसेप्टर पोटेंशियल, synaptic potentials, they are all examples of graded or local potentials, right? Now coming to the properties of action potential, आप एक mnemonic याद रखो, actor, amplitude, conductivity, threshold, obeys all or none law, refractory period. ठीक है, just remember the mnemonics. Actor, amplitude, conductivity, threshold, obeys the all or none law, and refractory period. So these are the properties of action potential. So first is that it can always be brought about by an threshold or adequate stimulus. Action potential can never be brought about by subthreshold stimuli. Suppose if the threshold stimuli is 5 millivolt, it will be brought about only by 5 millivolt or 6 or more than 5, but never 4. So it is always brought about by a threshold which is called as an adequate stimulus, which is called as the minimum strength of stimulus that will produce a response when it is given for an adequate duration. Okay, minimum strength of stimulus that will produce a response when it is given for an adequate duration. Second, it obeys all or none law. That means whenever you are giving a threshold stimuli, the action potential will be generated if will be always generated maximally. मतलब अगर कोई एक्शन पोटेंशियल डेवलप हो रहा है तो या तो वो मैक्सिमम रिस्पॉन्स देगा या तो वो जनरेट ही नहीं होगा. ठीक है, मतलब अगर जनरेट होता है तो वो मैक्सिमम रिस्पॉन्स है, और अगर नहीं तो जनरेट ही नहीं होगा. सो देयर इज नथिंग विच इज इनएडिक्वेट एक्शन पोटेंशियल, नथिंग विच इज इनएडिक्वेट एक्शन पोटेंशियल, दैट इज ऑल और नन लॉ. Action potential travels in all the direction away from the point of stimulus till the entire membrane is depolarized. So it is self-propagatory and amplitude is constant. That means the magnitude of the action potential, if it develops like this, it will always continue like this. ऐसे छोटा छोटा नहीं होने वाला है वो. There is no change in the amplitude, which is called as non-decremental. Now refractory period is very important. If you know that in the experimental lab also there are practicals which are pertaining to this and there are viva which come on this, तो ये वाला जो portion है इसको हम थोड़ा सा अच्छे से पढ़ लेंगे. I hope everything is very very clear up till now, है ना? ठीक है. हाँ. Now what is refractory period? So when you give a stimulus and the muscle will show a response. ठीक है, you gave a stimulus and the muscle will show a response. You will see that there will be a period after which the muscle does not, and not even muscle, any excitable tissue does not respond to the second stimuli. Okay, does not respond to the second stimuli. So when you give two successive stimuli, the membrane becomes refractory for a brief period. That means it does not give response to the second stimuli. This refractory period can be absolute refractory period and relative refractory period. So what is absolute? Absolute matlab the membrane is totally non-responsive and it will not give a response even to a supra-threshold stimuli. Okay, it will not give a response even to a supra-threshold stimuli. We will understand the causes. Relative refractory period mein the membrane will give a response only to a supra-threshold stimulus. Only to a supra-threshold stimulus, right? Not beyond that. So the absolute refractory period, ये कहाँ से कहाँ तक होता है? The absolute refractory period starts from the firing level to 1/3 of completion of repolarization. From the firing level to 1/3 of completion of repolarization, and it is not going to give response to any strength of stimulus. Relative, it will give a response only to a supra-threshold stimuli, and it is from the end of the absolute refractory period. Okay, from the end of the absolute refractory period to even the end of hyperpolarization, after hyperpolarization. Okay, so from the end of the hyper repolarization, the remaining period, end of after hyperpolarization. Right, so yahan tak you will be getting your absolute and relative refractory period. Now what is the ionic or what is the cause of that? See, you can see the absolute refractory period up to 1/3 of repolarization and the relative refractory period. Now here is hidden the cause of this. Now the cause of the absolute refractory period is basically the inactivation of sodium gates. ठीक है, you see that the sodium channels have got two important gates. One gate which is facing the exterior, matlab ECF, activation gate, also called as the M gate, and on the inside towards the ICF there is inactivation gate. These exist in three phases: resting, activated, inactivated. ठीक है, so in the resting state, that means when the RMP is minus 90 millivolts, these are actually ready to open. These are actually ready to open. How? Because the activation gate is closed but the inactivation gate is open. Remember, activation gate जो बाहर है, जिसको हम M gate बोल रहे हैं, ये इतना काम का नहीं होता है. This is not so very important in comparison to the inactivation gate. So ज्यादा important कौन सा है हमारे लिए? Inactivation gate. So जब RMP is minus 90, they are ready to go. That means inactivation gate खुला हुआ है. As soon as you give a threshold stimulus, you will see that the inactivation gate was open. The activation gate will now open and the sodium ions will easily enter inside. Now this phase from minus 90 to plus 35, see this phase from minus 90 to plus 35, when there is upstroke, as soon as you reach these upstroke or you cross the overshoot, you will see that although these M gates are open, बट नीचे के इनएक्टिवेशन गेट्स, जिसको हम H गेट्स भी बोलते हैं, ये बंद हो जाते हैं. So this is the period when there is absolute refractory period. So the cause of the absolute refractory period is the closure of the inactivation gates of the sodium channels. I repeat, the cause of the absolute refractory period is the closure of the inactivation gates. अब ये इनएक्टिवेशन गेट्स इतने टाइटली बंद होते हैं कि अगर अब आपने सुप्रा थ्रेशोल्ड स्टिमुलस भी दिया ना तो भी ये खुलने वाले नहीं है. राइट नाउ as you will see that as you slowly come towards from the depolarization and slowly you come towards after hyperpolarization and come towards RMP. तो जब आप RMP के तरफ आ रहे हैं, इसका मतलब जब आप relative refractory period के तरफ आ रहे हैं तो इनका कॉन्फ़िगरेशन दोबारा ऐसा हो जाएगा फर्स्ट जैसा, मतलब एक्टिवेशन गेट ओपन, एक्टिवेशन गेट क्लोज and inactivation gate open. And at this time if you give a stronger stimulus, you will be in the position to open the inactivation gates, right? So in the case of the relative refractory period, when they are trying to set back towards original, you will find that once you give a suprathreshold stimulus, the inactivation gates will open. So the basic cause of the absolute refractory period is the closure or the tight closure of the inactivation gates, and they do not open with any strength of stimulus. Relative में अगर आपने suprathreshold stimulus दिया तो you can open that, right? Potassium का कोई problem नहीं है. Potassium they exist only in two state. At -90 they are closed, and once you reach towards +35 they will open, right? Now this is the cardiac muscle action potential, where you can see that the absolute refractory period is very long, covering whole of the systole and even the beginning of the diastole. Okay, and you can see it is such a long absolute refractory period covering whole of the plateau phase. So iska significance hai ki because the cardiac muscles have got a very long absolute refractory period, they never respond to the second stimulus, and because of this they do not show tetanus. What is tetanus? Fusion of contractions. They do not show tetanus. The cardiac muscles cannot be tetanized. Okay, the cardiac muscles cannot be tetanized, and therefore they do not undergo fatigue. This question is asked in the Viva experimental lab में, right? So what is the significance? The impulse is always conducted from the presynaptic membrane to the postsynaptic membrane. It will never go behind, because behind the muscle or the tissue will be in the refractory phase. Okay, the traveling impulse does not depolarize immediately behind it because it is under the period of absolute refractory period. Just remember the duration of action potential: neuron 1 to 3 milliseconds, skeletal muscle about 2 to 4 milliseconds, heart, that is myocardium, 200 to 400 milliseconds, and the smooth muscle variable between 10 to 50 milliseconds. Now come to strength duration curve. Okay, this is also kept in the practical exam. इसको प्रैक्टिकल एग्जाम में भी रखते हैं, इसलिए आपको ये अच्छे से समझना चाहिए. So what is the strength duration curve? The intensity of threshold stimulus okay, the intensity of threshold stimulus and the duration of application of stimulus they are interrelated. So on the x-axis you are taking what is the stimulus ka duration, and on the y-axis you are taking what is the strength of the stimulus. Okay, so what is Rio base? Rio base is the minimum strength of stimulus. It is the minimum strength of stimulus that will elicit a response in the tissue. Okay, the minimum strength of stimulus essential for stimulating excitable tissue. What is utilization time? See, this is the utilization time. This is the utilization time. So what is the utilization time? It is the time needed. It is the time needed by a current of strength Rio base. By a current of strength Rio base to elicit response. ओके, टू एलिसाइट रिस्पॉन्स, मतलब जितना समय लगेगा रिस्पॉन्स प्रोड्यूस करने के लिए उसको आप बोलते हैं यूटिलाइजेशन टाइम. एंड व्हाट इज क्रोनैक्सी? C is equal to 2R. That is, chronaxy is twice Rio base and it is the measure of excitability of tissue. It is a measure of excitability of tissue. It is an index of excitability of tissue. अब इसको न्यूमेरिकली पढ़ते हैं तो वो काफी इजी हो जाएगा. नाउ सपोज देयर इज 1 मिलीवोल्ट का स्ट्रेंथ, नो एक्शन पोटेंशियल, 2 नो एक्शन पोटेंशियल, बट with 4 you are getting action potential. That means the minimum strength of stimulus which was needed over here is 3 millivolt and that is called as Rio base. Right? Now if this 3 millivolt is allowed to pass for 1 millisecond, no action potential. 2 millisecond, no action potential. But if you allow the 3 millivolt to pass for 2.5 millisecond duration, action potential is produced. So what is 2.5 millisecond? It is your utilization time. So the minimum strength of stimulus when given for adequate time, that is 2.5 millisecond, will produce a response and that will become your utilization time. Now double the strength of Rio base, double the strength of Rio base. Suppose आपने 6 मिलीवोल्ट दे दिया, मिनिमम कितना चाहिए था हमको 3, तो 6 मिलीवोल्ट को यदि आपने 1 मिलीसेकंड के लिए डाला, नो एक्शन पोटेंशियल. लेकिन 6 मिलीवोल्ट को यदि आपने 2 मिलीसेकंड्स तक दिया, you get action potential. That means 2 millisecond is chronaxy. Okay, 2 millisecond is your chronaxy. So chronaxy आपको टाइम बताता है, right? Remember, if the neuron has got least chronaxy, that means it is most excitable. Okay, if you say that the neuron has least chronaxy, that means it is more excitable. So the neuron is सबसे ज़्यादा excitable, followed by skeletal muscle, then your heart, and then your smooth muscle. Is there any significance? Yes, there is a very important significance. See, this is the normal strength duration curve and this is the strength duration curve of the injured nerve. So when the nerve will be injured, at that time this becomes very, very important feature that the Rio base is more, the time required, that means the utilization time is more, that means the excitability of the tissue is decreased because of the injury of the nerve. Right? Because of the injury of the nerve. So when there is injury of the nerve, at that time, you know, all these things are done. Matlab, at that time you take a graphical representation of the of the strength duration curve. Right? So I hope today we covered everything and all you understood also. That is the resting membrane potential. Right? The resting membrane potential, then the action potential, the effect of ions. I'll just also mention over here so that the topic becomes complete to us. What is going to be the effect of ions on RMP or on resting membrane potential or on action potential? So calcium का हमने already देख लिया, right? That if there is hypocalcemia, what will happen? The membrane excitability will be more. है ना? You are getting what? Paresthesias, you're getting spasm. Now, if there is an increase in the ECF potassium, that means there is hyperkalemia. What will happen if there is hyperkalemia? See, this is your ECF and this is your ICF. So if the potassium concentration over here is increased, what will happen? This gradient, concentration gradient will be lost because the potassium is already more in the ECF. The potassium which is present inside will not go outside because there is no need. ऑलरेडी बाहर इतना सारा पोटेशियम है तो कोई ग्रेडियंट ही नहीं है ना, तो अंदर का पोटेशियम विल नॉट गो आउटसाइड. इन दिस केस रिमेंबर दैट द मेम्ब्रेन विल बिकम easily excitable, isn't it? It will be very easy to make it towards action potential because the cell interior becomes less negative. Okay, the cell interior becomes less negative. That means the RMP significantly is less negative. So the fast threshold of excitation reach हो जाएगा और action potential. लेकिन अगर hypokalemia है, इसका मतलब if there is a decrease in the potassium ions inside, what will happen? अंदर का पोटेशियम बाहर जाता जाएगा, बाहर जाएगा, बाहर जाएगा. That means अंदर will be now more negative, hyperpolarized. अंदर क्या हो जाएगा? More negative या hyperpolarized हो जाएगा. और ऐसे conditions में muscle की excitability will be affected because if you are making inside more negative, then it will take time for that more negativity to reach a resting state, to cross the threshold of excitation, and then to form an action potential, right? If there is a decrease in ECF sodium, it is going to decrease the amplitude of action potential because the amplitude of action potential, that is the upstroke, depends upon sodium influx. So it is going to decrease the amplitude of action potential, but there is no effect on RMP. There is no effect on RMP because RMP का maximum contribution is by potassium. ठीक है, maximum contribution is by potassium. So I hope the lecture is very, very clear to you. Resting membrane potential, the different phases of action potential and the ionic basis of action potential. So tomorrow I'm going to start with probably neuron, classification of nerve fibers, structure of neuron, and then we will move towards the neuromuscular junction and so on, right? If there is any query, you can just write over here also. तो मैं उनको देख लूंगी and I'll try to answer them if they are very relevant and you feel कि मैम बता दो, तो I will definitely बताओ. ठीक है? So thank you very much boys and girls and make it a happy learning. Okay, bye bye and make it happy learning. Thank you. Good night.